Hi everyone and welcome to my talk on self-explainable classifiers and regressors in neuroimaging. Let me quickly start with a short brief motivation here. Most of you will know that machine learning tasks in neuroimaging are mostly either prediction tasks or exploratory tasks. In predictive tasks, we are interested in mapping our input image here, T1 image, with a deep artificial neural network to a specific clinical score or target variable like brain age or fluid intelligence. So it's a classification or regression problem. And an exploratory task is kind of related to generative modeling. We want to reverse this process by generating data for a specific score value for biomarker discovery or atlas or template generation. So both of those things are usually inverse direction of the same functional relationship between image and score. And most existing approaches in the literature ignore this kind of inverse nature, and they build individual unidirectional feed-forward models to solve both tasks in an isolated way. And our idea now is to do it in a bidirectional way by using a two-way bidirectional modeling. What does it mean? That means that we are bidirectional modeling the functional relationship by unifying predictive as well as exploratory modeling. So we have an invertible deep artificial neural network here, which can map from left to right to solve a predictive task like classification or regression. And on the other hand, we can also sample from this probability distribution here by using the inverse direction of the invertible deep artificial neural network. So we have a consistent model, one model, two directions, many applications. So it's kind of a multi-purpose model here. And it's kind of a generative classifier or regressor because we can generate data with the model. And therefore, it's an important step towards explainable AI, as we will see later on, because we can reverse or invert the decision-making process to explain the decision-making. And some technical aspects here, those are related to our workshop paper from last year. So our bidirectional model is based on specifically adapted normalizing flow technique. That means that we have a complex model that does this mapping from left to right here and right to left. It's composed of easily invertible parts, so a chain of simple functions. This is what's being used in normalizing flows, and it maps a complex data distribution, as you can see here, brain morphology variability conditioned on a specific factor like age, and maps it to a simple representation using a bijective function. And the representation here is what we call latent space, and it's a disentangled latent space where the first dimension of the latent space accounts for the task relevant part. So it's either the regression or classification target in the generative classifier or regressor, and then all the other dimensions of the latent space are irrelevant to solve the task, but they are needed to fully reconstruct the image so that we can generate nicely looking images. And it's a fully probabilistic model, so we use probabilistic optimization here, maximum likelihood optimization, and we can also generate data in a probabilistic way. So what we did here for this workshop paper is to build generative classifiers and regressors for two different problems, for brain age prediction and brain sex classification. So the models were asked to model the relationship between brain morphology as seen on T1 images of the human brain and age as well as sex. We used more than 5,000 T1 scans from a large database here, and we did a split here in training and testing cases, 4,300 for training and 700 for testing, and then built brain age regressor and a sex classifier, and compared our normalizing flow-based architecture or the accuracy of the architecture to standard CNN, a popular CNN from the literature, which has been used for both of those tasks. And as you can see here, for both tasks for age prediction as well as sex classification, you can see that our model here for the brain age prediction task reaches an accuracy of just below 5 years. An error between true and predicted age and the standard CNN is a bit more accurate, but those differences here are not statistically significant. And the same is also true for sex classification. So it's fairly accurate, and it's nearly as accurate as the standard CNN with the differences being not significant. But what we can now do with our invertible neural network here is to use it, or the inverse direction, to explain its decision. So a standard way of explaining decisions in CNNs, for example, is computing attribution maps or saliency maps, which are based on the gradient, or it's a gradient-based way of identifying important region. And in the standard CNN, we usually only have the forward direction. So we map the image to a specific age, for example, for brain age prediction. And then saliency maps are usually based on the gradient of this forward map. So for each voxel, we can then identify the important voxels and can either visualize the simple gradient, or do something like smooth grad or grad chem, and then visualize what are the important areas or voxels here for the prediction. But what we can now do with our bidirectional normalizing flow model is we can do it in a more natural way, or at least this is what we think, because we have the inverse direction available. So instead of computing the gradient with respect to all input voxels, we can directly manipulate the age, because we can compute the gradient or the partial derivative here with respect to age. So we can modify the age variable. And this is, actually has a geometric interpretation because this here is the tangent vector to the aging trajectory. And then we can map it back to the input space and visualize the important parts of the image that we use by our generative classifier or regressor in this case to render its decision. And we can see here, this is the result for our model here. Those are the results for gradient and smooth grad for the standard CNN. And you can see that the normalizing flow model comes up with a much smoother explanation of the important areas, and they totally make sense. So it kind of focuses mostly on the ventricles, which is normal because they are heavily used to come up with a specific age prediction here. Also in other models, as you can see here, but it's more noise down here. So we can generate smooth attribution maps by using the inverse direction. And what we can also do due to the invertibility of our model is something that we call counterfactuals. So counterfactual images represent an alternate reality. It's kind of a what-if scenario. So if we have a true or given original image at the age of 58 years, we can, for example, ask our model, why wasn't that one classified or predicted as being 35 years old? So, and can then generate an image which actually simulates this scenario. How can we do it? So we use the image of the same subject, or the result here is the counterfactual is the image of the same subject that would result in another prediction result, and we can do it by inverting the decision process. This is not being possible with standard CNNs because there we don't have the inverse direction available, but in our model we can do it because we have the inverse function here available, and we can change the age variable while fixing the intersubject variability, which encodes the age unrelated morphology of the patient, and then we can just simulate different age values here. And this again has a geometric interpretation because those images are just other points along the subject-specific aging trajectory, and then we can visualize them. So the original image here is 58 years, and it was perfectly classified or predicted by our brain age predictor here, and then we can ask them, okay, why didn't you say this image is 45 years or 75 years, so younger or older, and can generate those images. And we did it here, and you can see for a younger version, it would have, for example, expected to see smaller ventricles, which is what we already saw in the attribution maps, that the network is focusing on that part. And you can see for a 75-year-old subject, instead of 58 years as in the original image, it would have expected, for example, to see larger ventricles here. And we kind of did the same also for the brain sex classification task. You can see additional images in our paper, and it helps, for example, to identify misclassified cases or biases and stuff like that, because it's kind of a natural way for us to analyze results if you are able to look at images that look kind of similar to the input images, and then visualize the differences here, for example, by using different images. So let me quickly summarize what we did, or what I presented here. I presented a way to build self-explainable classifiers and regressors, which are based on normalizing flows to build those generative classifiers and regressors, and their accuracy is kind of comparable to standard CNNs for the tasks like age and sex prediction, but in contrast to standard CNNs, the decision-making process is reversible and modifiable, and this helps us to compute smooth attribution maps. But what is much more important, we can also compute counterfactuals, because we can modify the decision-making process and analyze, okay, what are possible what-if scenarios here. And what is also important to note is that those models are fully functional probabilistic generative models, so we can also use them for many, many other tasks. And that's it. Thanks for listening.